what would you say if I asked you, what is the big O of the function finding Nemo? Well, to make this a little bit cleaner, let's just remove performance done now because we've learned that it's not very, very important. And we can remove the console log as well. And looking at this and this loop, what would you say the big O is? In this video, we're going to learn about our very first big O notation. As we said, a runtime is simply how long something takes to run. How does this function and its runtime grow as our input increases? As our input goes from just a single item in an array, Nemo, to 10 items in an array, to 100,000. How does the efficiency of this function increase? If we look at this graph and we say we have 4 items in the array, well, the number of operations is going to be 4, right? Because we're going to loop through each item and say, is this Nemo? Is this Nemo? Is this Nemo? Is this Nemo? 4 times. No matter what, we're looping 4 times, at least with the way that we have this code set up. If we have 5 items in the array, it's going to be 5 operations, 5 loops. 6 is the same. 6 items is 6 operations. 7 is 7 operations. And 8 is 8 operations. Do we see a little bit of a pattern here? Well, we can draw a line through it. This is linear, right? As our number of inputs increase, the number of operations increase as well. And here, ladies and gentlemen, we've learned our very first big O notation. We say that the finding Nemo function has a big O notation of O n. That's a little bit strange. This is just a notation that you have to get used to. But we say big O of n, or what we call linear time. It takes linear time to find Nemo. Now, where does this n come from? This n can be anything, really. I could put x, I could put fish in here if I want. It's just an arbitrary letter, and we usually give n when it comes to big O. This is just a standard that you'll see across the board. N simply means the big O depends on the number of inputs, the number of fish. So if we just had the Nemo array, this would just be 1. If we had the everyone array, this would be 10. And if we had the large array, it'll be 100,000. But as the inputs increase, you see that the number of operations increase linearly with it. ON is probably the most common big O notation you'll find. If we go back to the graph, you can see that ON is right here in the yellow region that says fair. As the number of elements increase, you see that it's just a straight line. The number of operations increases by the same amount. Because keep this in mind, big O doesn't measure things in seconds. Instead, we're focusing on how quickly our runtime grows. We simply do this by using the size of the input, which we call n, or anything else that we want really, and compare it to the number of operations that increase. That's what scalability means. As things grow larger and larger, does it scale? So the find Nemo function is O of n, linear time. Another way to think about it is this. If we had a compression algorithm, let's say this function is this little compression, and the input is this little box. What's the big O notation of this function? Well, if we had one element, it will just compress one item. If we had multiple elements, again, we still have to run each box through the compression algorithm to compress the box. If we look at the function for the compress boxes, well, we're using the ES5 and ES6 syntax here, but we're essentially looping through each box And in our case, we're just console logging it. But you can see here that all of these, all we're doing as the input increases, the boxes, the number of boxes increases, the number of operations increase. And that is ON, linear time. Congratulations, you just learned your first big O notation. And this is probably the most common. But there's a few others. So, what other big O notations do we have other than linear time? For that, you're going to have to keep watching. I'll see you in the next video.